Okay, so you have another algebra proof before this guy in your notes. It has the middle column for you. You're going to want to work that, and we went over that in class together. So this is the one at the bottom of that page. Again, it's kind of the same process, right? Where we want to start by writing down the original equation. We always start with what was given to us. So we're going to start with our equation, and that's because it was given. And again, I keep saying this. Hopefully we all know how to solve an equation. And so you can probably just go through here and solve this thing all the way down. But remember, we're trying to give reasons for doing what we're doing too. So we know the first thing we want to do is distribute that 3. And so, boom, boom. And when we do, we'll get 14x plus 21 minus 3x equals negative 1. And the reason why we get to do that is because the distributive property says that we can do that and we still have an equivalent equation. Okay, from here, we're going to combine like terms or simplify. Is kind of what we keep saying. Okay, and you'll see something else pop up here, but I'm going to slide this over and just call this simplify still. Okay, and so we can ignore this guy here. Okay, length the same value we can ignore and just call this simplify. From here, okay, we're going to subtract 21, and this seems kind of perhaps a little monotonous, but I do want to keep writing this out. I want to show every step, right? And so we're subtracting here. And so therefore our reason for subtracting 21 from both sides, why do we get to do that, is because the subtraction property says we can. Okay? And then we simplify down again. 11x equals negative 22, and this is our simplify step. Okay? And then the division property, and I'm going to stop with the middle column at this point, says we can divide both sides by 11. And then, run out of room here, so up here, we're going to come down and say that x equals negative 2, and that's because we simplified. Okay, so that's what that proof should look like. And we can zip through all these other stuff, right? All right, some more properties that we want to try to use, and these are going to sound incredibly obvious, but we want to understand that they're there, and we can use them in our geometric proofs on down the line. So the first proof, first property is the reflexive property. Reflexive property just says that something is equal to itself. So for real numbers, A equals A. If we're talking about the length of segments, then we can say that AB, the length of segment AB is equal to the length of segment AB. And if you're talking about angle measures, we can say that the measure of angle A equals the measure of angle A. Now, of course that's true. There's going to be times where understanding this and realizing this and stating this is going to help us in proving what we want to prove. Okay? The reflexive property. If you're standing in a mirror, you see yourself. That's basically what this says. Okay? The symmetric property basically says that if A equals B, then B equals A. Okay? We can flip that equals around, and it's the same thing. Okay, it's the same, this little equation is the same on either side, and so we can do that for segment lengths too. So if AB, if the length of segment AB equals the length of segment CD, then the length of segment CD equals the length of segment AB. And for angle measures, if the measure of angle A equals the measure of angle B, then the measure of angle B equals the measure of angle A. Again, fairly obvious thing to have to state, but again, there's going to be a use for this. Okay, and then the transitive property. The transitive property looks a little bit like the law of syllogism from our deductive reasoning. It transitions from one numerical value to a third one going through a second one. And you should recognize this as a little bit like a law of syllogism. So where A equals B for real numbers, if A equals B and B equals C, then we can jump right to A equals C. So we're sort of transitioning through B to get to C. Okay, same thing for segment lengths. If the length of segment AB equals the length of segment CD, then CD equals EF, and CD equals EF, then AB equals EF, and you can see the same thing with the angle measures. Okay, measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then the measure of angle A equals the measure of angle C. Okay, and we can jump right to that. We know that automatically without having to measure them and check to make sure that they're the same. Okay, all right, that gets us to our first geometric proof. And geometric proofs are tougher than algebraic proofs because you don't always know exactly where you should be going next. This is the first time that I'll say this, but it won't be the last, right? You need to just write a statement down, right? When you get to a point where you think you don't know where you're going, look at your diagram, look at the statements in your proof, and just write what you know. And a lot of times that'll get you on the right path. If it doesn't, we erase it and we write down something else, okay? So, for example, we want to prove that segment CF, that the length of segment CF is equal to the length of segment AD. Okay? So the length of segment CF is equal to the length of segment AD. That's what we want to prove. Okay? So, how do we go about doing that? Well, in a two-column proof, you always start with some given information. Well, nothing was written over here at the side. Very often you'll have something like given and then some information, but we don't have that, okay? So instead we can go to our diagram, and our diagram gives us some stuff. Our diagram tells us that AB and EF are congruent, so that tells us that the length of AB is equal to the length of EF, and that's because it was given to us. So this guy is EF. Okay, our diagram also tells us that the length of BC the segment BC and segment DE are congruent, and so therefore the length of segment BC is the same as the length of segment DE. Okay, those are two given pieces of information. Now, where do we go from here? Well, we don't know yet, right? And so all I'm going to do is look around and see if I can come up with anything to write that I know is going to be true. And I don't know, maybe it'll help me, maybe it won't. Nothing really jumps out from here, okay? I can't do any substitution. There's nothing here that I can replace anything with. So what I do recognize is that the AB plus BC up here has to equal all of AC, the segment addition postulate, right? And so that's where this statement came from. We can use this segment addition postulate to make that statement. Now again, I don't know if that's going to help or not, but I'm going to write it down because I know it's true. Okay? Well, if it's true for AC, then it's going to be true for DF as well. I can do the same thing for DF. I can say that DF is equal to DE plus EF. And use the same reason, the segment addition postulate. Okay, great. How does that help? I don't know. We're just going to keep writing stuff. Okay? Well, I do have these two statements up here in our given, and DE is equal to BC. So I could replace BC here and AB here. And as a matter of fact, that's what we do in this next step. And the substitution property allows us to do that. Okay? Now, DF equals BC plus AB. What from here? Well, from up here, we see AB plus BC, AB plus BC, so I can take AC and substitute it in down there. I can just say that DF equals AC. And again, that reason is going to be by substitution. substitution property. Okay. So now I get this, DF equals AC. Okay. So right now I've got DF equals AC. Okay, well, didn't realize that, so that's kind of some interesting information. But it's not what I want to prove. Remember, I want to prove that AD and CF are the same. So, where from here? Well, there's this CD that's sort of stuck in between AC and DF. So I could add that measure to both sides of this equation. Right? I could add CD to both sides. And the addition property says that's okay. Okay, as long as we're adding the same thing to both sides of an equation, then it doesn't change the equation. So now what I'm looking at is AC plus CD, which gives me AD. And then I get DF plus CD, which gives me CF. So AD and CF. So I can substitute that in. DF plus CD is just CF. AC plus CD is just AD. And that's because of the substitution property. And if you look up here, that's exactly what we wanted to prove, and so we're done. Okay? So your first geometric proof, and it's a tough one, but this is the idea, where we just write statements that we know are true. Now they have to be true, and we hope that they get us where we want to go. Sometimes you're going to see it right away. And you're going to know what you're supposed to write. Okay? But very often you won't. And so we just write stuff down, and hopefully it gets us to where we want to go. It's got to be true stuff, and it's got to be right stuff, but that's it. Okay? I'll zip through this since we wrote it out together. Okay? All right. Prove angle. Now we're going to move into 2.7. We've got some angle pair relationships that we want to prove. And it'll get us into some theorems that we can use in our future proofs. Okay? The first one, right angle congruence theorem. The right angle congruence theorem suggests that all right angles are congruent. Okay? Well, that should sound fairly obvious, but remember that postulates are those rules that are accepted as being true, whereas theorems are those rules that need to be proven before anyone will accept them as being true. So this is a theorem, and we need to make sure that we go through and prove it. So what do? Well, we start with two right angles. So we're going to be given two right angles, and we want to prove that angle 1, that angle 1 is congruent to angle 2. So let's go do that. So two right angles. Angle 1 and angle 2 are right angles that was given to us. Well, because they're right angles, we know that the measure of angle 1 is 90 and the measure of angle 2 is 90. And that comes from the definition of right angles. If you go back through your definitions in chapter 1, you'll see that. Well, now we can do a little substituting. Since measure of angle 2 equals 90, and we find 90 over here, then we can just plug the measure of angle 2 in over here. And get the measure of angle 1 equals the measure of angle 2, and that's going to be by the substitution property of equality. Now, we don't have to say of equality. We can just say the substitution property. Now, because we know that these two angles have the same measure, then by the definition of congruent angles, we know that angle 1 is congruent to angle 2. And that's what we wanted to prove. So, now that we've proven this, now we know that all right angles are going to be congruent, because it doesn't matter what we call the right angles. We can change the names of angle 1 and angle 2, but if they're right angles, they're still going to be congruent by the same method every time. So what this means to us is, instead of going through all this process every time, if we know we have two right angles, we can just jump straight down and say they're congruent, and now instead of going through all of this, we can just say the right angles congruence theorem. Okay? So we can use this now. All right? Moving on. Little linear pair postulate. So postulate says if two angles form a linear pair of angles, then they are supplementary. We've already used this idea. Okay, we're just writing it down now. If two angles form a linear pair of angles, then they are supplementary. When are angles in a linear pair equal? Well, if they're supplementary, they have to add to 180. Remember that supplementary means they're going to add to 180. When are they equal? Well, when they're both 90. So in other words, when they are both right angles or 90 degrees. Okay, we'll use that idea as well. All right. Now we're going to get into something called the congruent supplements theorem. The congruent supplements theorem talks about if two angles are supplementary to the same angle or to congruent angles, then they are themselves congruent. Okay, now watch this. How do we know that? I'm going to do a quick little proof here. All right? Okay, watch this. If I've got angle 1, angle 2 here, and I'm going to stick angle 3 right in the middle. Okay? Now watch this. Let's say that angle 1 and angle 3 are supplementary. And angle 1 is 80 degrees. Well, that means that angle 3 has to be 100, right? Because they have to add to 180. So I know that angle 1 and angle 3 are supplementary. Well, if I also know that angle 2 and angle 3 are supplementary, then if angle 3 is 100 degrees, that means angle 2 has to be 80. And look at this. Angle 1 and angle 2 have the same measure, and so therefore angle 1 is going to be congruent to angle 2. This is one idea of your congruent supplements theorem. Is if two angles are supplementary to the same angle, then they're going to be congruent. Okay? Now, what if we know, let's see, we're going to talk about angle 1 again and angle 2. Now let's talk about the fact that we've got two other angles, angle 3 and angle 4, that are congruent. Okay? So angle 3 and angle 4 are congruent. What if I told you that angle 1 and angle 3 are supplementary? And the measure of angle 1 was 80. Then that means the measure of angle 3 would have to be 100. Right? Well, because 3 and 4 are congruent, that means angle 4 is going to be 100 degrees as well. Now what if we knew that angle 2 and angle 4 were supplementary? Now 1 and 2 are not supplements to the same angle. They're supplements to different angles, but they're supplements to angles that happen to be congruent. So if angle 4 is 100 and angle 2 and 4 are supplementary, that means angle 2 has to be 80. Well, look, these angle 1 and angle 2 are congruent again. And so we can say angle 1 is congruent to angle 2. Okay? So if two angles are supplements to the same angle, or if two angles are supplements to two other angles that happen to be congruent, then they themselves will be congruent. And that's called the congruent supplements theorem. That's what this guy is saying. So if 1 and 2 are supplementary and 3 and 2 are supplementary, then 1 and 3 are going to be congruent. We just saw why. That's how we use it. Okay? Same thing goes with complements as well, and we call it the congruent complements theorem. But we can change all of those examples I just gave you. We can change those from being supplementary to complementary pretty easily, and everything would still turn out the same. Right? If two angles are complements to the same angle or to congruent angles, then they themselves are going to be congruent. So if 4 and 5 are complementary and 6 and 5 are complementary, then that means 4 and 6 have to be congruent. Okay? Think long and hard about those two examples I just gave you, and hopefully you wrote those down. If not, go back and write those down because with the actual angle measures, because I think it'll help this make a little bit more sense. These two theorems are always theorems that give students a hard time. Okay. Moving on. Sketch and label vertical angles. Remember, vertical angles share a vertex, and they make an X, right? So you need two lines that cross, basically. So you got an X. Okay, and then we can label them angle 1, angle 2, angle 3, and angle 4. Remember, we can always use numbers to name our angles. Okay, so 1 and 3 are your vertical angles here, and so are 2 and 4. Those are the angles that make an X when you trace them. Okay, we could trace this guy here and this guy here, and now I've got an X. Or I can trace this guy here and trace this guy here, and I still get an X. So those are your vertical angles. Okay. Sketch and label linear pair of angles. Well, if I've got angle 5 here, then another angle, angle 6, needs to share that side and help form a straight line or a straight angle. So their non-sharing sides need to form a line. Boom, oops, boom, boom. Okay, and that's a linear pair. Angle 5 and angle 6 are a linear pair of angles. Okay, now vertical angles. Something interesting happens with vertical angles. Turns out that there's a theorem that suggests that vertical angles are congruent. That's a theorem, so we need to prove it. Okay, so we've got these vertical angles here. We've got angle 5 and angle 7 that are vertical angles. Okay, well, we start there. Angle 5 and angle 7 are vertical angles. That was given to us. Okay, now 5 and 6 are a linear pair. So are angles 7 and 6. They're a linear pair as well. It's a definition, and that's just the definition of a linear pair, and they're shown in the diagram here. Okay? Now, if they're a linear pair, that means angle 5 and angle 6 are supplementary. Angle 7 and angle 6 are also supplementary. Okay? That's from the linear pair postulate that we just saw. Well, since 5 and 7 are both supplements to the same angle, they get to be congruent, and that's by using this congruent supplements theorem that we just talked about for a few minutes. And so therefore 5 and 7 are congruent, so vertical angles must always be congruent. We just proved the theorem, so now we can use it. And again, the idea behind proving the theorem is you don't have to go through this every time. Okay? As a matter of fact, now that we have proven this theorem, if we know that two angles are vertical, we can jump down to say that angle 5 and angle 7 are congruent, and we can use the vertical angles. Congruence theorem. Okay? And that's it. So we're basically building up our toolbox here to continue to help us write our proofs. Okay? All right, that's it for this particular lesson. We combined this with the previous video to help get the rest of 2.5 in. And we'll talk about some more proofs out of section 2.6 next time.